series of lecture. This is the second lecture of the series. In this lecture also we'll be revising the simplex method before we discuss revised simplex method. So in this lecture we'll be solving one more example so that your understanding of the simplex method becomes somewhat clear, and then we'll go on to discuss the revised simplex method. So we'll start with a problem. So this is a maximization problem of z equal to 2x1 plus 5x2. This is the objective function subjected to three constraints here. In the previous problem there were two constraints, so here there will be three constraints. So three slack variables will be introduced here. So these are the constraint equations subjected to x1, x2 greater than equal to 0. So we'll write the canonical form of these equations. We'll represent it in the canonical form, and this is the canonical form of the problem that has been given here. So I have introduced three basic variables. You can introduce as x1, s2, s3. You can write it as x3, x4, x5, doesn't matter. So these values x1, s2, s3 has to be greater than 0 like x1 and x2. Now, as I have said that in a simplex method, you have to start with the initial basic feasible solution. So initial basic feasible solution in this case, or in other cases also, we start with the variables in the objective function x1 and x2, or any other variables if it is there, all equating to 0, and s1, s2, s3 becomes equal to the total resources that is available. This is s1 is equal to 24, s2 is equal to 21, s3 becomes equal to 9. So this is my basic feasible solution. Mind you, this is not an optimal solution. We will check whether this is an optimal solution or not. Obviously this will not be an optimal solution because z will be equal to 0. So therefore we find out and check whether this is an optimal solution. On finding out that it is not an optimal solution, we will iterate, and after iteration we will again check whether that is an optimal solution, and the process goes on until and unless we find an optimal solution. So we'll start with the first table, that is with the initial basic feasible solution, where s1 is equal to 24, s2 is equal to 21, s3 is equal to 9. So s1, s2, s3 are the basic variables and x1 and x2 are the non-basic variables. Remember my two statements in my earlier lecture that all the aij's of the basic variables will be an identity matrix, and the cj minus zj of the basic variables will be 0. This has to be 0. If it is not, then you have made some mistake. Remember, this is a checking method, and with this I am forming the base of the revised simplex method, because in revised simplex method we will be dealing with the identity matrix and the cj minus zj. So this is the basic feasible solution, and this is the first table that I have constructed. So these are the s1, s2, s3 are the basic variables, and you can see if I form a matrix of the basic variables, sorry, I'm not very good with this pen, please bear with me. Okay, so this is an identity matrix. This will always be an identity matrix. The aij's of the basic variables will always be an identity matrix, and we'll see that cj minus zj of the basic variables will also be equal to 0. So here you can see here 2, 5, 0, 0, 0 are the coefficient of the variables x1, x2, s1, s2, s3 in the objective function, and cb are the coefficient of the basic variables in the objective function, that is 0, 0, 0. These are the basic variables, so the coefficient of that basic variables in the objective functions are 0. So this is the 0. So we have started with s1 is equal to 24, s2 is equal to 21, S1 is equal to 9. So this is my initial basic feasible solution. Now I'll check whether this is an optimal solution or not. For checking this, we all know that we have to find out the Zj and we have to find out the Cj and find out the difference of the Cj minus Zj. Okay, so finding out that, we have to find out the Zj, which is the summation of Cb. So Zj will be 0 into 1 plus 0 into 3 plus 0 into 1, it will give us 0. So this is my Zj, and similarly we will find out the Zj for all the columns, and Cj minus Zj will be equal to 2 minus 0 is 2 and 5 minus 0 is 5. Now whether this is an optimal solution or not, for that we have to check all the Cj minus Zj. All the Cj minus Zj has to be checked. Now from all this we see that at least one of the values of Cj minus Zj are positive. So therefore this solution is not optimal. And the one having the maximum value will be the pivot column. So therefore x2 will be the entering variable. So x2 will enter somewhere around here. It will replace s1, s2 or s3, either of them, either of these three. So x2 will become a basic variable. Currently it is a non-basic variable, and x2 will become a basic variable. Now the question is, which basic variable it will replace, or in other words, which one of s1, s2, s3 will become a non-basic variables. So for that, so we know this is the pivot column. So all the aij's of the pivot column will be using, or will be dividing the b by the aij of the pivot column. So 24 by 4 is 6, 21 by 1 is 1, 9 by 1 is 9. So all the values of theta here, whichever is the less will be the exiting variable or the pivot row. So S1 will be the exiting variable, and this will be my pivot row. So this we know. So x1 will be replaced by x2. Okay, now we'll iterate towards the next solution. So how to iterate? As I have said, for the pivot row, all the aij's will be divided by the pivot cell value. That means 1 will be divided by 4 to get 1 by 4. So 4 will be divided by this 4 itself. So we get 1. Again, this is by design, because we want to make it 1. Because we want to make this column and one of the column of the identity matrix. So this has to be a 1. So this one will be 1 divided by 4 will equal 1 by 4. Okay, so 1 by 4 here. So 0 divided by 4 will be 0, and 0 divided by 4 will be again 0, and 24 divided by 4 will be 6. Sorry. Okay, so here we have the iterated pivot row in the next table. Now I want to find out the other two rows. Now for finding out the other two rows, we require to find out the fixed rows. I again repeat, what is the fixed row? Now my objective is that in the pivot column, these values in the next table will be 0. As it is 0 here, This is by design. We want to make it 0. Now to make it 0, and for finding out the values here, these values, these values, these values, this value, this value, we have to multiply by a fixed ratio. Now 1 minus 4 into a fixed ratio here, so that it has to become 0. So 1 minus 4 into x equal to 0. So x will be equal to 1 by 4. So this is 1 by 4 here. And similarly, this is also 1. So 1 minus 4 into x equal to 0. So x is equal to 1 by 4. So the multiplying factor fixed ratio is 1 by 4. Now to find out the other rows values here. So this is 3. So 3 minus 1 by 4 into 1 will give us 3 minus 1 by 4, that is will be equal to 11 by 4. So this is 11 by 4. So next one, 0 minus 1 by 4 into 1 is equal to minus 1 by 4. So this is minus 1 by 4. So similarly 1 minus 1 by 4 into 0 will be 1. So this is 1. So 0 minus 0 into 1 by 4 will be equal to 0. And 21 minus 1 by 4 into 24 is 21 minus 6, that is equal to 15. So likewise, we have found out the third row also. So that gives us 3. Now we'll check whether this is an optimal solution or not. To finding out this is an optimal solution, we will find out the Zj and Cj minus Zj. Now Zj is equal to 5 into 1 by 4 plus 0 into this plus 0 into this will give you 5 by 4, that is 1 by 4. So likewise, we have found all the Zj, and if you multiply by subtract these values from the Cj, we get 3 by 4 minus 1 by 4 likewise. So this is a positive value, so therefore it is not optimal. Of all the Cj minus Zj, we have 1 as a positive value, therefore this is not an optimal solution. But we know that this is the entering variable, so x1 will be the entering variable, and it will become a basic variable, and it will replace either of these three. Which one it will replace? We'll divide this b by the corresponding value of the pivot column. So this is 6 divided by 4, it will become 24 here, and 15 divided by 11 by 4, it becomes, I think, 60 by 11, something like that. And 3 divided by 3 by 4, it becomes 4. So I think this is the lowest value. So this is the exiting variable. X3 is the exiting variable. X3 is the exiting variable. So X3 will be replaced by this X1. And remember, in previous case, S1 is replaced by X2. So value of coefficient of X2 in the objective function is 5. So in this CB we have written as 5 here. So likewise, here S3 will be replaced by X1, and the CB of X1 is 2. So here it will be 2. So we'll move on to the next slide. Okay, so again we'll iterate to this, and we'll get this. We get the fixed ratio as 11 by 3 and 1 by 3. So again we test for the optimal solution, and we'll see that all the Cj minus Zj are less than 0. So therefore this is an optimal solution, and we have the solution as x2 is equal to 5 and x1 is equal to 4, and the optimal solution z equal to 33. So this is my solution. You can put the value of x2 and x1 in the objective function and check, it will come out to be 33. So this is how we solve simplex method. So with this knowledge of the simplex method, we'll go on to learn the process of solving linear programming method by revised simplex method. So I thank you for listening and watching this video patiently.